Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Today we'll continue from where we stopped last time about the one compartment open model for intravenous bolus administration of drugs. We discussed the pharmacokinetics of such drugs that follow this one compartment open model when they are being administered by intravenous bolus. So we'll just have a quick review for what we previously explained, and then we will explain in detail once we come to the new slides. Okay. The last time we explained what's the definition of IV bolus injection, and simply we said IV means the drug is injected into the vein, into one of the peripheral veins, and then bolus means that we will give it rapidly. It is a rapid injection, not a slow one. Okay? And then last time also we explained the assumptions of one compartment open model for one compartment open model for IV bolus injection. And we said one of the most important assumptions for one compartment open model that the drug is rapidly distributed throughout the body. The drug is rapidly distributed throughout the body. Okay, that's why we consider it as one compartment, because the drug immediately distributes to the whole body. As we see in this photo, we give injection and then there is no drug in the body at the beginning, and then after administration immediately the drug is distributed all over the body. So the body is behaving as one compartment. We don't have different rates of distribution to different parts of the body. So we consider it as single uniform component. Okay, so this means the drug to be distributed quickly to the body, and the body behave as single uniform compartment. This means that there is rapid equilibrium between the drug in the tissues and the drug in the in the blood. Okay. So there is rapid equilibrium between the drug in the blood, where we introduce the drug by IV route, and then the drug in peripheral tissues. And we explained that to be rapidly distributed doesn't mean that it is uniformly distributed. It doesn't have the same concentration in all the tissues. So it depends on the physical properties of different drugs. We may have different concentration in different tissues, but what we reach is the equilibrium. The rapid equilibrium means the movement of the drug is not one way anymore. Okay, before equilibrium, as we explained in the model, the drug is moving from blood to the tissues till we reach the equilibrium point. Then it is two-way. We call it open model also because the drug can enter and leave the body, and since the drug is distributed quickly, rapidly to all the body tissues, including the drug eliminating organs like liver and kidney, then elimination process also will occur immediately upon entering the body and follows first order kinetics. Okay. And we explained last time what do we mean by first order kinetics. We explained the model also. We represent the body as one compartment. This compartment has an amount of drug in the body, and it has a theoretical volume. We call it volume of distribution. Theoretical, not actual one. The drug is given by IV route. Since it is given rapidly, there is no rate of administration, so we don't put here any rate constant, but the drug is eliminated from the body following first order kinetics, and here we have K is the first order elimination rate constant. First order elimination rate constant. We explained last time what is zero order process, what is first order process, and so on. I'll just focus now on the first order process, which is followed by elimination here. And here we can represent the rate as equal to constant times a factor to the power 1. Okay. So when we talk about elimination rate, we will represent it as elimination rate equal to elimination rate constant times A. Here, the factor is the amount of drug in the body. When it comes to elimination, A is the amount of drug in the body. The characteristics of first order elimination, first order kinetics, as we mentioned, is that the drug doesn't have a constant rate of elimination with time. Rate of elimination with time decrease, as we explained last time. We mentioned that when we last time made, like, for example, we checked the slope. We wanted to see the slope. We found that we have a decreasing slope with time. The annotation is not working, so I just cancel it. So we found that if we look here at the slope, we find that the slope is decreasing with time. We explained it last time. The slope is decreasing means the rate of concentration decrease with time is decreasing. It's not a fixed rate. Why? Because it is factor dependent. It depends on the concentration factor. Okay, it depends on the concentration. So while with time the concentration is decreasing, the rate of elimination also decrease. And it gives only linear, it gives a linear relationship only when we plot ln the value of the factor with time, ln the value of concentration with time. Okay, so when you plot ln concentration versus time, you can get a linear relationship. Same also when you get when you plot log concentration. Okay, the rate constant can be calculated graphically from the slope. The rate constant equal to the slope here is negative since the concentration is decreasing with time. So the slope is a negative value, but rate constant is always positive. So how to get the positive? Negative, negative is positive, right? So say the slope is, for example, if, for example, the slope is, let's say the slope is 0.2, negative 0.2. Then K will be equal to negative 0.2. So will be equal to 0.2. Okay. We already explained about 0 second order and these issues last time, so we'll not stop by them now, but we will move to the most important things related to what we explained today in our lecture. So we already explained this part about what is the difference between the two sides. Here, the slope is bigger than here. This means that there is a faster rate of decline of drug concentration. Okay, and then we explained that decreasing the concentration, having a curved line like this means that the rate of decrease of concentration decreases with time. So it depends on a factor. So it means that there is a change in the slope, means there's a change in the rate of elimination, and the slope is decreasing with time as I showed. So this means that rate of elimination is decreasing with time, because it depends on one factor, that is drug concentration. So with time, once the drug concentration decreases, the elimination rate also decreases. Okay, so now the calculations for drugs that follows first order kinetics, what we are going to do is that we will plot ln CP. CP is the concentration of drug in plasma. We will plot it versus time. So we get concentration versus time plot, ln concentration versus time plot. This one has a straight line. This is it will give a straight line. So the first thing we can calculate from this curve is the reaction concentration rate constant, elimination rate constant. Okay, first thing we can calculate is the elimination rate constant. How to calculate it? We calculate it as negative slope. You remember from mathematics, slope equal to y2 minus y1 divided by x2 minus x1, right? And so what to do is just you can mark any 2 points on the line. These points will have y and x, or x and y. X is time and y is the drug concentration. So just mark 2 points and then get their x and y. How much is the concentration and how much the time of this concentration? So this one we can say x1 and y1. And the second point is x2 and y2. So instead of writing x1, y1, x2, y2, it is time 1, concentration 1, or CP1, and T1, time means time in the second point, and concentration in the second point, CP2. So if you want to calculate the slope, this is actually here, concentration, the one that gives linear relationship is ln the concentration, not the concentration itself. So when I write y1, I write ln CP1. And if I write y2, I write ln CP2. So here the slope is y1 is, so remember this one, don't forget. You get a linear relationship, not when you plot concentration versus time, but you get linear relationship when you plot ln concentration versus time. So here y is ln concentration. So y2 is ln CP2. And y1 is ln CP1 divided by T2 minus T1. This should be the way to calculate the slope. Okay. So how to reverse? How to, instead of getting, of course, here, since okay, now since ln CP2 is bigger than ln CP1, is smaller, sorry, smaller than ln CP1, and T2 is smaller than T1, we will get a negative value, and then just remove the negative, then you get the K. Okay? Or to directly calculate K, we can reverse either in the numerator or denominator, numerator or denominator. So we can say, for example, the same equation. We can use the same equation, but for K, we can say equal to ln CP2 minus ln CP1, but in the denominator, instead of T2 minus T1, we make it T1 minus T2. In this way, you can get directly a positive you can get a positive value, which is K. Okay, So in this way, you can get a positive value, which is K. So if we want to transform the same if you want to transform the same equation, we can write it in this way. The equation was K equal to ln CP2 minus ln CP1 divided by, instead of T1 minus T2, we can say delta T. Okay? So you can transfer T here. So you get ln CP2 minus ln CP1 equal to K times T, or delta T. And then you can move this one to the other side. You change it to positive value. So you'll get this form finally, ln CP2 equal to ln CP1 minus KT. Okay? If we assume that this one is so ln CP2 minus ln CP1 divided by T2 minus T1 is equal to negative K, because this is the slope. So you move the other side, and then you will get the equation that ln CP2 is equal to ln CP1 minus KT. And then when you do inverse ln is the exponent when you write it in Excel, right? You make it like this. Exponent, we make it E without this dash. So inverse ln will give you CP2 equal to CP1 times, no ln here, so we make it exponent. So times the exponent of negative KT. So now we have different forms of the equation. You can calculate K. If you know K, you can calculate CP2 if you know another level on the graph. For example, if I give you 2 points, I tell you that, for example, I tell you in a problem that you have given certain dose of a drug by IV, and then you got that the concentration, say, for example, 3 hours and say 7 hours was this value and this value, for example. Okay? And I ask you to calculate the concentration, say 9 hours, or say 10 hours after the injection. I want to calculate the level here. So I can calculate K from the graph, and after I calculate K from the graph, then I will after calculating K from the graph, then I can use this equation to calculate CP at 10 hours as CP2. I can calculate it using the value of K, the time between the 2 points, and the concentration in the other point, whether the one at 3 or the one at 7 hours. Okay? We will solve some problems and we will practice, we'll see how to do. The second thing I can get from the graph, other than calculation of k, which is equal to negative value of the slope, you just reverse or inverse the sign, is I can extend back the line. You can extend back the line to the intercept. Your intercept here is equal to the concentration in the plasma at time 0. We can call it CP node. We call it CP node. And this CP node is the one that we use for calculation of the volume of distribution. We use it to calculate the volume of distribution. So if I give you a set of data for several concentrations, at least 2 or more is better, at different time points after administration of IV bolus injection, and they ask you to calculate the pharmacokinetic parameters, like elimination rate constant, volume distribution. I ask you to calculate the concentration at another time that is not given to you in the set of data. Then you can just draw a graph. You plot lung concentration versus time. You get a line. You extend your line back. You can determine the concentration, how much at time 0, CP node, means when all the drug inside the body, but elimination has not started being yet. This is the first point. And you can calculate K from the slope. You can calculate volume of distribution by dividing those by CP. And graphically, you can, if I ask you, I want the concentration, for example, at 9 hours. So this is 9 hours. Okay, this is 9 hours. So you just graphically, at 9 hours, how much the concentration? You just extend the line here and see how much the concentration at 9 hours. Okay, from this graph, you will get ln the concentration, not the concentration itself. So just inverse the value, inverse ln for the value. You get the exponent of the value. Then this is the concentration at this time, 9 hours. Okay, and you can do mathematically using this equation. Okay, you can do mathematically using this equation. So I can, for example, if I know how much the concentration at, say, 7 hours, then I say ln concentration at the second point, which is CP at 9 hours, equal to the concentration at 7 hours times exponent of negative K times T. How much T here? T is a delta T. How many hours between 7 and 9? We have between 7 and 9, we have 2 hours difference. So T equal to, delta T equal to 2 hours. Okay, this is the way we calculate. We will have some practice. We will solve some problems and see how to do it. Okay. You can also plot, instead of using Excel, for example, and ln CP versus time, or doing it on a graph paper, ln will have so many fractions. So some people before the use of computer and these things, they used what we call it semilog paper. They used semilog paper. This is a semilog paper. Okay. Why we call it semilog, not log? Because we have X and Y. One of them is normal scale. You see here 0, 1, 2, 3, 4, 5. Each distance is 1 hour and the distance is equal, right? So this is the normal scale. But the y-axis, if you see here, 1, 10, and 100 is written. See, the distance between 1 to 10 is same to 10 to 100. Is that normal scale? Cannot be normal scale, right? So why is it like this? Because actually this is a log plot. The distance here represents the log value, not this written value actually. So log 1 is, as you know, 1 equal to 10 to the power 0, right? So log 1 equal to log 1 equal to 0. Log 10 equal to 1. Log 100 equal to 2. So actually this is like 0, 1, and 2. So now became logical. Distance between 0 and 1 is equal to the distance between 1 and 2. So actually this Semilog paper is this Semilog paper is what? Although the digits written are the normal numbers, the normal digits, but actually the scale is based on log value of the written digit. So the scale for drawing the graph here is based on the log value of this digit written here. Okay? Hope it is clear. So if you just, even in Excel, if you just used, instead of plotting ln CP versus time, you plotted log CP versus time, then usually the slope is different by a factor of 2.3. 2.3, actually this is the factor to convert ln value to a log value. Okay? So the factor to convert ln to log is 2.3. So we divide by this factor to convert back the log into ln. Okay, so you multiply the ln by 2.3, then you get the log. You divide the log by 2.3, you get the ln value. Okay, so from here, this is the equation of the linear function. Do you remember from algebra, we write the equation as y equal to, let's say, b plus ax. This is the intercept. This is the slope. This is the x. So if we replace x is time, the slope is k, and it has a negative value, right? Negative k, the slope. B is the intercept. Intercept is CP naught. Ln CP naught. If we write log, then we have to divide the k by 2.3. Y here is log concentration in plasma at any time. Okay? Okay, instead of writing concentration at any time, we can write concentration too. It can be actually calculated from concentration before it. So if you determine two concentrations, the same equation we can use. This is CP2, CP1, and this is CP2. You can calculate CP2 from CP1 using the same equation. Log CP2 equal to log CP1 minus k divided by 2.303 times E. Or you can convert it into okay, if you are doing manual, you are using this Semilog paper, then you just determine the concentrations graphically, as I say, just determine the time at any point in the graph, how much the concentration, and determine the concentration. by calculation, then you can just use the equation concentration here, C2 equal to log CP2 equal to log CP1 minus K divided by 2.303 times T. So which one we are going to use? We are going to use the easy one. We don't need to use the log. Even you are using this paper. So you are going to even you are using a Semilog paper, you don't need to use this equation. So we make life simple by calculating the slope. Even I don't need to use these factors 2.3 and so on. Even you are using Semilog paper. So just determine 2 points. You determine 2 points. Once you read the value, actually, it is the absolute value. It's not the log value. So just get the concentration, how much. So you have C1 and C2. And determine their time. Time 1 and time 2. Then when you need to calculate K, just make calculation of K very simple as that. K equal to. And then use the previous equation, ln CP2 minus ln CP1 divided by, instead of time 2 minus time 1, we make it time 1 minus time T1 minus T2. So in this way, you can get the value of K as a positive value. If you want to calculate the concentration mathematically at any time point, then you just use the previous equation we used, C2 equal to C1 times the exponent of negative K times delta T. So which point to use as C1? Any of these. You can use any of the previous points on the graph as C1. And delta T is the time between the point you choose and the point you want to determine its concentration. This is delta T. So for example, here from 1.75 hours to 3.25 hours, 3.75 hours. So the difference between them is delta T is 2 hours. That is the way to calculate. I hope it is clear. If you have any question, anything you don't understand in the middle of my explanation, you can just raise a hand. Or you can just open your audio and ask me, okay? So now we talk about this pharmacokinetic parameter K that we call it elimination rate constant. This is the proportion between the rate of drug elimination and the amount of drug in the body or drug concentration. So it is a proportion between the rate of drug elimination and the amount of drug in the body. This is the equation we wrote before. The equation was rate of elimination equal to K times the amount of drug in the body. This is the or concentration of drug in the body, but we have to, mainly should be amount of drug in the body. And this is related to the concentration of drug in the body as well. The proportionality between them is volume of distribution. We explained it. So just we look at this simple form, rate of elimination equal to K, elimination rate constant, times amount of drug in the body. So in this case, K will be equal to what? Would be equal to rate of elimination divided by the amount of drug in the body, right? So K here is the proportion between the rate of drug elimination and the amount of drug in the body. Understood? Okay. So you divide rate of elimination. The rate of elimination is amount per time. It's a rate of elimination. So amount of drug eliminated per unit time. So say, for example, it is milligram by divided by hour. And the amount of drug in body is in the same units of the amount of drug in the rate of elimination. So if you use milligram in the amount of drug in the body. So milligram. So when you divide a milligram by milligram per hour by milligram, what is the unit remaining? So let's write it. So let's divide amount of rate of elimination is in milligram per hour. In other words, you can say milligram times hour to the power minus 1 divided by amount of drug in the body by milligrams. You can delete or cancel these against each other. So the unit remaining for elimination rate constant is time to the power minus 1, hour to the power minus 1. Okay? Hour to the power minus 1. Okay? So here, K is the first order rate process constant. Actually, it is the sum when we calculate, just we observe the decrease of drug concentration in the body and the decrease in amount of drug in the body with time. So elimination usually is maybe due to different processes of elimination, maybe metabolism, maybe excretion, maybe both together. So we just calculate in this way by watching the decrease of drug concentration in the body, or calculating the total elimination rate constant. But this one can be actually fractionated, into smaller case. For example, metabolism rate constant and excretion rate constant. Okay? Okay, now another question is, does the rate constant, elimination rate constant, change with the change in the excretion? No. With changing, sorry, the concentration of drug in the body, no, it doesn't decrease. It is a constant. The rate is decreasing with the decrease in the amount of drug in the body. They decrease together by the same proportion. This proportion, elimination rate constant, remains constant. It doesn't change. So be careful, be aware of this. Because the amount of drug in the body change over time, the rate of drug elimination change by the same proportion, okay? And the proportionality between them remains constant. The proportionality is between rate of elimination and amount of drug in the body remains constant. So elimination rate constant remains constant in case of first order elimination. So this one happens in first order elimination in drugs with linear pharmacokinetics. Okay, so I explained this one to you in the graph already, how to calculate the elimination rate constant. You can calculate using two lines, either on a semi-log plot or non-CP versus time plot. If you calculate it from the equation using log CPs, then you have to divide by the slope by 2.303 to convert the log into log. If you calculate it from ln CPs, then you don't need to convert. This is just K is, you reverse the negative sign of the slope, then you get a positive value that is K. Okay, as I explained already. Now we go to the next pharmacokinetic parameter, which is the apparent volume of distribution. And from the title here, we can see we call it apparent. Apparent means it's not a real value, it is a theoretical value. Appears to us by simple calculations. It represents the volume that must be considered in estimating the amount of drug in the body from the concentration of drug found in the sampling compartment. Say, for example, sampling compartment is the plasma. So you have concentration of drug in the plasma. CP, okay? The volume that can give you the concentration of the concentration of drug in the plasma to be calculated from amount of drug in the body is, we call it the volume or apparent volume of distribution. It's not a real one. Why not real one? Because, as we mentioned, concentration of drug in the plasma may not be equal to the concentration of drug in the heart, may not be equal to the concentration of drug in the heart. So it is just a theoretical volume, not a real volume. Okay? So the same equation that you know from chemistry, that is the volume the same equation that you know previously from chemistry, which states that volume equal to what? Amount of solute divided by concentration, isn't it? And concentration equal to amount of solute divided by the volume. And the amount of solute equal to the concentration times volume, isn't it? So just here the solute is the drug in the body. Concentration is, if we use the concentration of drug in plasma, then the volume is the volume of distribution. So you can say volume of distribution equal to amount of drug in the body divided by concentration of drug in the plasma. This is the way we calculate the volume of distribution. So as we mentioned, it's not an actual volume. It is a theoretical volume, apparent volume. Why? Again, because it depends on calculation of the amount of drug, depends on it, because it is calculated as a proportion between the amount of drug in the body and concentration in plasma, while the drug concentration in other tissues may be different, so it doesn't represent the actual volume where the drug distributed in the body. Okay? So it is a proportion between the dose and concentration of drug in plasma. So now how to determine it experimentally? At what time you can know definitely how much the amount of drug in the body. If you give drug by intravenous route, it is at CP node at time 0, immediately after being injected. So how to calculate volume distribution? As I showed before, this graph, you extend the line, you get the CP node, you get the CP node, and amount of drug in the body at time 0 is the dose that you give. This amount you know already. Okay, so you divide the dose by CP node, then you get the volume of distribution. So experimentally, how we determine the volume distribution? We divide the dose, which represents, because bioavailability for IV is 100%, right? So we divide the dose given by the CP node. We get the volume of distribution. VD equal to amount of drug in the body divided by CP node. So this is a general equation, amount of drug in the body equal to volume distribution times CP. When I write it as CP node, then it should be equal to the dose given by IV bolus, divided by volume of distribution, or volume distribution equal to dose divided by CP node. You can write here volume distribution, and instead here you write CP node. Okay? This is the way we determine it experimentally. So, as I explained, you will back extrapolate the line, the straight line. You will back extrapolate the straight line, and then you will just to determine the CP naught, and you know the amount of drug in the body at time 0, which is the dose given, so VD equal to dose divided by CP naught. And the most important pharmacokinetics when you answer problems, you have to be careful about the units, okay? So for example, the dose, you cannot use the dose in gram while the concentration is in milligram per liter. Both should be in milligrams. So here milligram per liter. If the concentration milligram per liter, then your dose should be in liters. If your concentration in milligram per mil, for example, then your volume distribution is in milliliters. Have to be careful about this. Okay. Another pharmacokinetic parameter to explain today is the area under the curve. And we explained it before. We said the area under the plasma concentration versus time curve is a representation of drug exposure. So we mentioned that if we give bigger dose, more amount entered the body, then the area under the curve would be larger, right? So if you give a smaller dose, then your if you give a smaller dose, then the concentration will be smaller, then the area under the curve will be smaller, right? So in this case, you will have a yes, you have a lower AUC. You will have a lower AUC. Okay? Okay. So AUC is used in toxicology. It can be a measure of drug exposure. Used in biopharmaceutics to compare bioavailability of different products. So, for example, you give 2 tablet formulations at different times, and then one tablet formulation gave you a curve like this. The other one gave you a curve just like this. Which one has better bioavailability or higher bioavailability, A or B? Okay, so you can compare their bioavailability using the AUC. As you see, definitely the AUC under the formulation B is less than the AUC under formulation A, isn't it? So we can conclude that formulation A is more bioavailable compared, or has larger bioavailability compared to formulation B. It's used in pharmacokinetics to estimate other pharmacokinetic parameters. We can use it to calculate bioavailability and clearance. Okay? We can use it to calculate bioavailability and clearance. So how do we calculate the area under the curve? How do we determine the area under the curve? Okay. Area under the curve is determined by something we call it trapezoidal rule. Trapezoidal rule. Okay. So have to be careful. Why do we need to use trapezoidal rule? Because the curve, it is a curve, it's not a line, it's not a linear relationship. When you calculate area under the curve, so we calculate it based on the concentration versus time curve, not lone concentration versus time curve. So be aware of this, take care of this, don't forget. When I ask you to calculate the area under the curve, don't make a lone CP versus time plot. No, we have to plot the absolute values of the concentration. We have to plot the absolute values of the concentration. Okay? We have to plot the absolute values of the concentration. So, why do I have to use the trapezoidal rule? Imagine with me, this is your curve, you make it like this. This is a common mistake I see with the students. They will just determine the first concentration, and then, for example, a concentration here, and then they consider it to be like this. They calculate the area of all this. Okay, they consider it one space. So this is the error. See this area, the difference between the straight line and the curved line, this is an excess. So now your error is very big. Your error is very big in calculation of the area. To avoid this, what do? We have our curve like this. Okay? So we divide into small trapezoids. Here they consider it one trapezoid in this shape. They consider it one trapezoid. They get a very big error. This is an extra area included in the calculation of AUC, but it should not be. So instead, I just divide into small trapezoids. And then I calculate the area of each trapezoid alone, and then I add them together. So actually, when you calculate the area of this trapezoid, actually to get accurate calculation, this line should be a straight line. But actually it is not a straight line, it is a curved line, right? But having small trapezoid like this, the difference is very small. So the error is smaller. The error is smaller. So you don't just consider the whole shape as one trapezoid, you just choose one point at the beginning, one point at the end, and then calculate the volume of one trapezoid. If you calculate the area of one trapezoid, then this is your error margin. Error margin is very big. The error in calculation is very, very big. Okay, so just divide into small trapezoids, and then we calculate the area of each trapezoid alone. So how to calculate the area of the trapezoid? You remember when you have a rectangle, what to do? When you have a rectangle, we multiply the length by width, right? Okay. Now in the trapezoid, we have two lengths. We have L1 and L2. One is bigger than the other. So actually, I multiply the average. So the average is L1 plus L2 divided by 2. You multiply by the width. Okay, so what is the length here? The length is the y-axis. Y-axis is the CP. So it is CP1 plus CP2 divided by 2. Okay? And then what is the width? The width is, say, for example, here T1 and the end of the trapezoid is T2. So this is the distance between them is T2 minus T1. This is the no negative actually, so you can just say T1 minus T2. Okay, just the distance between them, the absolute value, the positive value. So you calculate for each trapezoid the area, and then you add them together, then you get the sum. Okay, so if you use this value, you will calculate up till the last measured concentration in your data, CP last. So how about the triangle till infinity, the remaining triangle till infinity? How to calculate this remaining triangle till infinity? Okay. The area of that remaining triangle till infinity is equal to CP last divided by K, equal to CP last divided by K, equal to CP last divided by K. So you calculate the sum for all the trapezoids in order to calculate the area under the curve till the last measured concentration. To calculate the area under the curve till the last measured concentration. And then you calculate the area under the curve from last measured concentration into infinity using this equation. AUC from last measured concentration to infinity equal to CP last concentration in plasma, the last measured concentration of drug in plasma divided by K. What is K? Elimination rate constant. And then you sum these two together. The first part, we call it AUC from time 0 to the last measured concentration, to last. And the second part is AUC last to infinity. Then you calculate the area under the curve. From area under the curve, you can calculate clearance. Clearance can be calculated by different ways. Clearance equal to the K times the volume of distribution. Clearance is AUC divided by dose. So clearance, what is clearance here? This is another pharmacokinetic parameter we can explain. Is a measure of drug elimination from the body without identifying the mechanism or process. We same like elimination rate constant. There is hepatic clearance. We call it CL. Hepatic. There is renal clearance. We call it CLR, for example, renal clearance. Okay, and there is total clearance, CLT, total clearance. Okay. Drug clearance is defined as the volume of plasma fluid that is cleared of drug per unit of time. So it's a measure for how many liters, for example, of the volume distribution of the drug that will be cleared per unit of time. And this unit of time is usually hour. So the unit will be volume per time. So the unit will be, for example, liters per hour or milliliters per minute. Okay, this will be the unit of the clearance. Okay, the rate of drug elimination is divided by the plasma. The rate of drug elimination divided by the plasma drug concentration. equal to the clearance. So clearance is equal to rate of elimination divided by Cp. It's a first order process. In first order kinetics, it is a constant regardless of the drug concentration, same as K. Okay, so same as K, clearance is constant. Why it is constant? Actually, there is another equation for clearance. Clearance can be calculated as equal to K times Vd. Before we mentioned that K is constant. Volume distribution for the drug also is constant. It doesn't change with time. So clearance also ultimately will be constant. Okay? And also it can explain the first order kinetics. We said in first order kinetics, rate of elimination decrease with time. Now clearance represents a fixed volume of fluid, of plasma, say for example, cleared from the drug for every unit of time. Since the drug concentration in this volume will decrease with time, then the amount eliminated from that fixed volume will be decreasing, means the rate of elimination is decreasing. So again, I say, imagine that clearance is 3 liters per hour. Say, for example, for certain drug, imagine that the clearance is 3 liters per hour. Okay? And then this means that every hour, 3 liters of the volume of distribution will be cleared from the drug, right? Means that every hour, 3 liters of the volume distribution will be cleared from the drug. So first hour, maybe concentration is, for example, 10 milligram per liter. So the 3 liters will have 30 milligrams. So we will lose 30 milligrams of the drug in the first 3 hours. So the rate of elimination in the first 3 hours is 10 milligram per hour. Say after that, the concentration became 5 milligram per liter. When you lose, at the beginning, 3 liters per hour, so 30 milligram per hour will be lost. So at the beginning, the rate is 30 milligram per hour will be lost. In the second hour, the concentration, say, decreased to 5 milligram per liter. So in this case, when you clear 3 liters, then you lose 15 milligrams. So in the second hour, the rate of elimination is 15 milligram per hour. Say after this became 3 milligrams per liter. So 3 liters will be cleared. So you get rid of 9 milligrams per hour. This is the elimination rate. So you can see this concept explains also the dependence of the rate of elimination on the drug concentration in plasma in first order kinetics. Okay, so up till now clearance is constant, elimination rate is constant clearance is constant and elimination rate constant was also constant in case of first order elimination. Okay, volume distribution is constant, doesn't change. So what changes with time? What is concentration dependent? What is dependent on the amount of drug in the body? It is the rate of elimination. So clearance can be calculated as equal to K times the volume distribution, elimination rate constant times the volume distribution, and also it is equal to dose divided by AUC. So if you give certain dose to an individual, you can take the samples and determine the concentration over time, and then you can calculate the area under the curve. You know already how much dose you give, then you can estimate the clearance equal to the dose divided by AUC. Okay, what is the unit? The unit is K is hour to the negative -1. Vd is in volume units, maybe liter, maybe ml, so it is milliliter per hour. Liter per hour, milliliter per minute, depends on the units used when you calculate. But it is always the unit of volume divided by the unit of time. Okay. Now we go to the, I think the last elimination, the last pharmacokinetic parameter we'll discuss today, which is the half-life of elimination, or just say elimination half-life, the T half of the drug. This is the time the concentration will take to reach its half its value. So it is the time taken for plasma concentration to fall to half its original value, and it is time. So we measure it in hours, minutes, and so on. Okay. T half actually is a fixed, in first order kinetics also, T half is a constant. It doesn't change with the change in concentration. If you remember last time I explained to you that in first order kinetics, the rate of elimination decreases with time, but the proportion of decrease is fixed. It decreases at a fixed proportion. Okay? And I explained to you last time. And we made, I think, a table like this. And we say, for example, every 3 hours, it will become half its original value. For example, at time 0, the concentration was, say, 10. 3 hours later, it became 5. 3 hours later, became 2.5. 3 hours later, became 1.25. So here, the 3 hours actually, since it is divided by 2 all the time, means T half is equal to 3 hours, right? Because all the time become half its original value. Let's calculate the rate of elimination. Here in 3 hours, from 10 to 5 means 5 divided by 3 hours, so something like 1.66. Rate of elimination here in, say, the dose in milligrams, so the concentration milligrams, so say milligram per. Actually, you have to multiply by volume distribution to get the amount of drug in the body. Say volume distribution is 10. Say VD equal to 10 liters. So if the concentration is 10, means the amount of drug in the body is 100. Okay? So amount of drug in the body equal to 100, 50, 25, and then 12.5. If you calculate the rate of elimination, so you decrease from 100 to 50. So it decreased 50 divided by 3 will give you something like 16.66, say. And then in the second 3 hours from 50 to 25, you lost 25 over divided by 3 will give you only 8.33. In the second interval, the other 3 hours from 25 to 12.5 lost only 12.5 in 3 hours, means you lost 4.1, probably 6, and so on, almost, okay? So you can notice it that the rate of elimination is decreasing with time, but the proportion is fixed. At the same time interval, the amount lost or removed from the body is the fraction removed is the same. The fraction removed is the same. Usually, whatever, irrespective of how much is the half-life of the drug, but in the first, after one half-life, concentration become 50%. We lost 50%. This is another calculation you see here. And after 2 half-lives, we lose 50% in the first half-life and 25% in the second half-life. So total 75%. So 99% of the drug is almost removed after about 7 half-lives. So you can consider by after 7 half-life, the drug is almost completely removed. Or sometimes to make life easy, they consider by 5 half-lives, almost all the drug is removed since 96.87, almost 97 of the drug removed from the body. Okay. How to calculate elimination half-life? Simply by this equation, T half equal to 0.693 divided by K. Where did we get this equation from? Consider that you have a concentration and it's half. You say delta T equal to ln CP2 minus ln CP1 divided by K. Remember the original equation, K equal to this numerator divided by this denominator. So denominator divided by numerator. So we just changed the position. So this is the form. You remember from the mathematics, ln number minus ln another number, you can say equal to ln CP2 divided by CP1, right? Divided by K. So actually the relationship between them is 2. And if you get the ln of 2, then it is equal to 0.6993. Okay? So it is ln 2. This value is equal to ln 2. Actually, the equation was ln CP 1 minus ln CP. Okay, divide by T2 minus T1. We make it like this. So we get that time. Delta T here is T half. When we say T half, then the ratio between these two is 2. So ln 2 is 0.693 divided by K. This is T half. How to get it graphically? Just determine any concentration and divide by 2. How much is its half? Maybe this point. So determine the time at this point, the time at this point. The time between them is the T half. Okay, this is graphically how to do it. Determine 2 points of concentration at different times, and the ratio between them should be 2. One of them is double the other. And determine the time interval between these concentrations. So this is the T half. Let's practice, let's solve some problems and see how to answer the questions. So like this, in practical life, you do a study, you give certain dose by IV bolus, for example, here in this problem, in a study, they gave a 500 milligrams. And then they collect blood samples at different time points, and they measure the concentration in these time points. And they found that these are the concentrations at different time interval. They ask you to plot and determine CP1, calculate, they ask you to calculate K and VD. Okay, calculate K and VD. So as we explained before, in real life, actually, the extra point we explain here, in real life, you will not get that all the points exactly on, if you just plot on a similar paper like here, or even you calculate ln of the concentration and then you plot ln concentration versus time, you will not get the points exactly on a straight line. So there is a technique, maybe you know from secondary school, we'll do in the tutorial. So next time, please bring with you the next session, bring with you similar papers. We'll practice how to use it to draw the curves and then to do the calculations. So you try to get some central line that will have same variation from almost all the points. You try to make it in the middle, passing by the maximum number of points you can, and similar number of points on the right side and left side of the line. So you extend this line should represent the data. And then you determine any two concentrations that must be on this line. You don't take from you take from your data if they are on the line. Okay, so you determine 2 points on the line, for example, here and this one. So we consider this one C1, this one is C2 or CP1, CP2, but for short we make it C1, C2. You determine the time points, T1 and T2. Okay, when you are using the semilog paper, actually the scale is log scale, but when you read the values, the value actually is the absolute value. So we read from here, for example, that the concentration say is 20, say 30. And say here we read that the concentration say 15. Okay. So you have C1 and C2, 15 and 30, and then you determine the time. Say, for example, the time is 3 hours and 6 hours. Then you calculate K equal to, you don't need to use log here because I have the value of C1, the absolute value. So I just say ln C2 minus ln C1 divided by, instead of T2 minus T1 to get a positive value, I just say T1 minus T2. And then you calculate the K. Okay, calculate volume distribution. You just back extend the line, determine the intercept, how much is CP naught, and then VT equal to the dose that you give divided by CP naught. Okay, that is the way you should do the calculation. So here we determine 2 points at, we just to give ourselves, just take it easy. Since you will extend, you determine CP naught, you can use CP naught as your C1 and use another point as C2. Okay, and CP naught at time 0. That's very simple thing. So CP naught here is 87.1 at time 0, and CP2 is 4.17 at 10 hours. You calculate K, this is the value of K. Since the time in hour, then K must be in hour to the power negative 1. Volume distribution, dose divided by CP naught. So this is CP naught 87.1, and the dose in the problem is 500, so it is 5.74. Why liter? Because the concentrations in microgram per ml. Microgram per ml actually is equal to, take care, is equal to milligram per liter. So straightforward, I can assume this is milligram per liter. So I use the dose in milligram, and then the concentration, I assume it is milligram per liter, so the volume will be in liter. So here is milligram per liter is equal to microgram per ml. But I consider it milligram per liter because the dose is in milligrams. Okay, calculate clearance equal to K times volume distribution, 0.304 times 5.74 equal to 1.74. The unit is, volume distribution was in liters, and K was in hour to the power negative 1, so this one should be in liter per hour. Calculate the T half. T half equal to ln 2.693. If you forget this value, remember ln 2 divided by K. So equal to 0.693 divided by 0.304. So it's almost something like 3. 3 point something. And the unit will be hour, because K power to the power -1. Okay? Example 2, what is the concentration of drug 0, 2, and 4 hours after a dose of 300 milligrams? Known pharmacokinetic parameters are parallel volume distribution is 20 liter, initial rate constant is K, and then, and the initial rate constant K is 0.15 hour to the power -1, and use this equation. Or without even asking to use this equation, they tell you that they give a dose of 300 milligrams by IV bolus injection. The drug is following, in the problem also to write it complete, I should write for you the drug is following linear pharmacokinetics and the elimination is first order elimination. So they want the concentration at 0, 2, and 4. So how to calculate? At time 0, I can start with time 0. So C P naught equal to, as we know, it is equal to the dose divided by V equal to 300 milligrams divided by volume distribution, which is 20. So equal to 15 milligram per liter. The volume distribution in liter, the dose in milligram, so milligram per liter. Done. Calculate the concentration at 2 and 4 hours. So I can calculate CP2 at 2 hours equal to CP1, which is CP node here, times exponent of K, negative K times T, equal to 15 exponent K is 15, negative 15, times T. T here is delta T, as you mentioned. What's the time between 2 hours and 0 hours? So the time is 2 hours between the two concentrations. So if you calculate it, you should get this value. CP4, same thing. You can use two ways to calculate CP4. I can say 15 times exponent of, this is CP node. What is K here? K is 0.15. Okay. So negative K 0.15. Okay, times. Here I use CP node. So the time between CP node and 4 hours is 4 hours. And I get the result. You should get this one. You can calculate it also from the concentration at 2 hours. So I can say CP4 equal to CP2 times exponent of negative KT. So equal to 11.11 exponent of negative K times the time. The time between 2 hours and 4 hours is 2 hours. You should get also the same result. Okay. The third example is if CP2 6.2, CP6 is 3.7 milligram per liter, the dose is 500 milligram IV bolus, then what are the values of K, V, and CL? So we can calculate so many things. Number one, K is the easy one to calculate. So K equal to ln, we make it easy, ln C2 minus ln C1, or ln C1 divided by C2, divided by T1 minus T2. We reverse 2 minus 1, 1 minus 2 to get the positive value. So ln the first concentration, how much? The C2 second concentration is 3.7 minus ln 6.2 divided by T1 is 2 hours minus 6 hours. Okay, and then you should get this value. Second thing is calculate volume distribution. To calculate volume distribution, you need CP node. So how to calculate CP node? I can calculate, since I know K, I can calculate from this or from this, from any of them. So you can say CP node equal to, you remember before the second concentration equal to CP node times So when you convert the equation, you make Cp naught equal to Cp2 divided by. So if I calculate from the one at 2 hours, then it should be 6.2 divided by e to the power negative k, 0.129, times the time. How many hours between concentration at 2 hours and the Cp naught, 2 hours. So you should get this value. If you get Cp naught, that's easy. You can get the volume. You can get the volume distribution. V equal to dose divided by Cp. So we just converted this equation. Huh? So equal to, the dose is 500 divided by Cp naught 8.03. So you get this value, 62.3. Calculate the clearance. Clearance, as we mentioned before, equal to elimination rate constant, K times volume of distribution, equal to 0.129 times 62.3. Should give this value. If you want to calculate the half, just 0.693 divided by K. Point 693 divided by K. Okay. Another problem. Let's. I leave this one till the end. This one simpler. We answer this one first. What is the IV? What IV bolus dose is required to achieve plasma concentration of 2.5 microgram per ml at 6 hours after the dose is administered? The initial rate constant is given, apparent volume distribution is given. So here they want the dose to achieve certain concentration, but they didn't give you the Cp naught, the easy one. So you have to calculate first how much is the Cp naught. And from Cp naught and volume distribution, you can calculate the required dose. So what to do is calculate Cp naught first, equal to Cp2 divided by e to the power negative k time. So here you have the concentration 6 hours after the dose. And we said before, microgram per ml is equal to milligram per liter. So equal to 2.5 milligram per liter divided by e to the power negative k. K is given here, 0.17. What's the time between Cp naught and the one at 6 hours? 6 hours. You should get this value. If you get this value, then you can calculate the dose required should be equal to Cp naught, which is 6.66 milligram per liter, times volume of distribution, which is given in the problem as 25 liters. Then should be equal to this value. Those should be given 166.4 milligrams in order to achieve this concentration 6 hours after administration of the dose. I will leave example 4 for the next for the tutorial. Next session, whether it is written as tutorial or lecture, just bring with you some log papers, and then we will answer this problem and do some plotting of data on Semilog papers. We practice how to use them for calculation, and then we can proceed to the next topic. Okay. Any question before I close the session? Any question before I close the session? Okay, then we can conclude. Assalamu alaikum wa rahmatullahi wa barakatuh.